All right, how are you guys doing this morning?
Doing good.
Cool deal. Well, today we're going to talk about second order filters. And then shortly after we finish up with that, I'll finish making out your homework assignment and post that for you guys. And it'll cover first and second order passive filters. But before we get to that, I've been made aware that the drop date is tomorrow. And so I will have your exam ones graded for sure by tomorrow. If anybody is able to get me their exam 2 by 10 a.m. tomorrow, I will make sure that it is graded in a timely fashion so that you can use that to also determine whether or not you should stay in the class. And I will get as many homeworks as I can done, but honestly, if it'll be like 5 if you're lucky. So one homework, exam 1 for sure. Hopefully 5-ish homework assignments, and then exam 2 if you turn it in, and that should give you a good idea of how you're doing in the class and all that kind of jazz. So, all right, if I don't lose my mind because of the cricket that's making noise in my room, I will be in good shape for today. So let's start talking about our second order filters. All right, so second order filter is one that contains 2 energy storage elements, as we discussed on Tuesday. The one that we're going to look at today, sorry, let me find my notes here, looks a little something like this. Excuse me. And we can effectively do the transfer function, at least a first order approximation of it, by inspection, right? We know it's going to be V out divided by V in, and we can use voltage division again, just like before. So it should be pretty easy to understand that our transfer function H of omega, at least in the denominator, is going to have 1 over j omega c plus j omega L plus R. And in the numerator, since we're applying voltage division, it's just going to be the voltage drop over the resistor. So that would just be R. And then we would divide both sides by V in, which is how we can get the transfer function directly. I'm going to simplify this by multiplying by a factor of j omega c and so that's going to give me 1 minus omega squared LC plus j omega RC in my denominator, and then a j omega RC in my numerator. So that is my simplified transfer function. Because we have a second order filter, instead of just having corner frequencies, or a corner frequency or multiple corner frequencies, as we'll see momentarily, we also have what's called a resonance frequency. So our resonance frequency omega naught, which is the exact same thing we use to describe our resonant frequency in series and parallel RLC circuits during our transient analysis, occurs when the transfer function is purely real. So we're looking for a specific frequency at which our transfer function will be purely real. And we can actually figure that out by observation in this problem, right? And so what I mean by that is if the real part of the denominator, 1 minus omega squared LC, were 0, then our transfer function would be j omega RC divided by j omega RC, which is just 1. So that is a real value. So from that, we can see that our resonant frequency is simply 1 over the square root of LC, which is exactly what we observe for our series and parallel RLC circuits. So there's going to be a lot of familiar things here when we're dealing with second order circuits. And that might make sense, like on Tuesday, I don't know that I mentioned it, but we saw that the corner frequency of our RC filter was 1 divided by RC, which is exactly the inverse of the time constant for an RC circuit. And you should see the exact same thing in your homework assignment when I have you look at an RL filter. You should see that the corner frequency is going to be R over L, which is exactly the inverse of the time constant there. All right, so we can play around with this transfer function h of omega and split it up into a rectangular form that we can use to determine both its magnitude and its phase angle. So revisiting h of omega here, where we're going to have 1 minus, sorry, no days yet. We multiply this by the complex conjugate of the denominator. So that would be 1 minus omega squared LC minus j omega RC. And that same thing in the denominator here. What we get is, in our denominator, 1 minus omega squared LC squared plus omega RC squared. And let's see, the real part of this guy is going to be omega RC squared. And we're going to have positive j omega RC multiplied by 1 minus omega squared LC divided by that same denominator, 1 minus omega squared LC squared plus omega RC squared. And we can use this rectangular form to find our magnitude. So it's going to be the real part squared plus the imaginary part squared. Sorry, this should be squared there. And if we do all of our math here, let's see, so in the numerator, we are going to have omega RC to the fourth plus omega RC squared 1 minus omega squared LC squared. over 1 minus omega squared LC squared plus omega RC squared, this whole thing squared. And I think I have enough room to do the factoring that I need to do here. So I can factor out an omega RC squared, and that will leave me with omega RC squared plus 1 minus omega squared LC squared divided by 1 minus, come on pen, there we go, omega squared LC squared plus omega RC squared squared, and this guy cancels out the squared there, and this leaves us finally with omega RC divided by the square root of 1 minus omega squared LC squared plus omega RC quantity squared. Alrighty, so that is our magnitude. Now let's talk about those pesky corner frequencies. So our corner frequencies, as before, will occur when the magnitude of our transfer function is equal to 1 divided by the square root of 2. So what I'm going to do here, real quick, draw a line, is I'm going to take my magnitude function and divide it by omega RC over omega RC. And so I'm going to have 1 divided by the square root of 1 minus omega squared LC quantity squared. And when I move my omega RC underneath the square root sign, I'm going to have omega RC quantity squared plus omega RC squared over omega RC squared. And this looks like 1 divided by one, and I'm trying to figure out at what frequencies this equals to 1 over the square root of 2. So I can say then that 1 minus omega squared LC squared divided by omega RC squared plus 1 is equal to 2, which lets me further write that 1 minus omega squared LC squared is equal to omega RC squared. And now I'm going to say that 1 minus omega squared LC is equal to plus or minus omega RC. And that's going to effectively, I can manipulate this to get 2 different quadratic equations, okay? So if I put LC as 1 over omega naught squared, what these guys simplify to is omega squared plus or minus R over L omega minus omega naught squared is equal to 0. This is a quadratic equation, and I'm going to get two solutions. Omega C1. So this is my low frequency, is going to be negative R over 2L plus the square root of R over 2L squared plus omega naught squared. And my high corner frequency, omega C2, is going to be positive R over 2L plus R over 2L squared plus omega naught squared. Or actually, let me move the square to the outside. So, do any of you guys remember what we call the quantity R over 2L for a series RLC circuit?
I mean, isn't that alpha? I can't remember like what the actual name is.
Yeah, no, that's exactly what I was looking for. That's alpha. So we can see that our corner frequencies are very, very similar to the natural frequencies of a series RLC circuit. So in a series RLC circuit, we had negative alpha plus the square root of alpha squared minus omega naught squared, or negative alpha minus, and we're effectively, instead of getting the positive, so we expected S1 and S2 to be negative frequencies because we wanted to see a negative exponential decay. Here in our filter circuits, we're expecting to see the positive values of those frequencies. So it's effectively like multiplying the whole thing through by a factor of -1 is how we get these numbers. So those are our corner frequencies. Let me put a box around those guys. For this particular filter. And I think we haven't done the phase angle just yet, but I think if we look at this magnitude function up here, we could identify what type of filter this is. So by that, I mean, let's look at what happens when H is equal to 0. Excuse me. So when H is equal to 0, our magnitude function at omega is equal to 0, what value does our magnitude function have?
Zero.
Yeah, so we're going to have 0 in the numerator and 1 in the denominator. 0 divided by 1 looks like 0. What about when we allow omega to approach infinity?
Infinity.
So infinity over infinity squared, which is 1 over infinity, which is also
0.
So if we have 0 at very low frequencies and 0 at very high frequencies, what type of filter is this?
Bandpass.
Exactly right. So this is a band pass filter. I would, so on your third exam, I'm going to have you guys design a circuit, a filter circuit that would effectively tune into Louisiana Tech's radio station KLPI, which I think has a frequency of 89.1. I'll have to double check that. And because it's an FM radio station, it has a bandwidth of 200 kilohertz, I believe, yeah. So actually now, since I've mentioned the quantity of bandwidth, let's talk about what a bandwidth for a low pass filter is, and I'll sneak that in right here. So for, for our bandpass filter, our bandwidth is defined as omega C2 minus omega C1, because that's the band over which things will pass. And our omega naught, our resonant frequency, is actually the center frequency for this system. So based on just this stuff that I've given you here, it should be rather trivial to design a bandpass filter with a specific center frequency and a specific bandwidth. All right, so let's move along to, I did all this on page 3 somehow? Well, that sucks. Let me add another page. All right, so now let's talk about our phase response. It's always going to be the inverse tangent of the imaginary portion over the real portion. So if we look at this guy right here, we can see that it should be omega RC times 1 minus omega squared LC. Divided by omega RC squared, which is going to give us the arctangent of 1 minus omega squared LC divided by omega RC, and we can cancel out our C's if we were so inclined. 1 minus omega squared L over omega R is what our phase response should look like. All right, so that's a bandpass filter. Let's look at a slightly different filter. So on this guy, we're taking our output voltage over two components. Our inductor, which has an impedance of j omega L, and our capacitor, which has an impedance of 1 over j omega C. So our transfer function here should be R plus j omega L plus 1 over j omega C in our denominator. And then we'll have j omega L plus 1 over j omega C in our numerator. And let's multiply through by a factor of j omega, j omega C over j omega C here. All right, so j omega L times j omega C is negative omega squared LC. So this is going to look like 1 minus omega squared LC in our numerator. And then we're going to have 1 minus omega squared LC plus j omega RC in our denominator. So it looks vaguely familiar here. Let's talk about our resonant frequency here. How are we going to make this purely real? So if we look at what we did the last time, we wound up with a a magnitude of 1/1 effectively, or 1 at resonance. This time we're not going to be able to do that. So if we look at this guy, when 1 minus omega squared LC is equal to 0, then we're going to have 0 divided by an imaginary number, which is 0, which is still a totally real response. So in this case, we can see that our resonant frequency, omega naught, is still 1 over the square root of LC. So in the previous example, our resonant frequency occurred where the amplitude was at its maximum. And in this case, our resonant frequency is occurring where our amplitude is at its minimum. But it's all about whether or not the transfer function is purely real or not. That's what defines the resonant frequency. All right. So from that, we can manipulate our transfer function further. So we will have pinky finger messed things up. 1 minus omega squared LC plus j omega RC, 1 minus omega squared LC. Multiply this by the complex conjugate of the denominator again, 1 minus omega squared LC minus j omega RC times 1 minus omega squared LC minus j omega RC. And this is going to give us, in the denominator, 1 minus omega squared LC squared plus omega RC squared. And in the numerator, we are going to have 1 minus omega squared LC squared minus j 1 minus omega squared LC times omega RC. So it's looking very similar to what we saw for our bandpass filter. We can take the magnitude excuse me. And 1 minus omega squared LC squared here. Square this whole thing. Since I'm squaring it, I'm not going to bother keeping up with that negative sign. So we're going to have 1 minus omega squared LC squared. Sorry, not squared there. Omega RC squared. And doing the indicated math, we are going to have 1 minus omega squared LC squared multiplied by 1 minus omega squared LC squared plus omega RC squared divided by 1 minus omega squared LC quantity squared plus omega RC squared. Sorry, this thing squared, this guy cancels that squared, and we are left with 1 minus omega squared LC divided by the square root of 1 minus omega squared LC squared plus omega RC squared. So our corner frequencies, I want to take a look back at what we had here. The reason why I'm taking a look back at this is because we're going to wind up with exactly the same situation, except that I would put my plus or minus sign on the 1 minus omega squared LC side and leave just positive omega RC. So what's going to happen is we're going to have the exact same corner frequencies. So I don't really feel the need to go through and derive all of that again. So we would see that omega C1 is equal to, negative R over 2L plus the square root of R over 2L squared plus omega naught squared, and omega C2 is equal to positive R over 2L plus the square root of R over 2L squared plus omega naught squared. So same exact values here. While we're at it, let's look at this guy and figure out what happens when we look at omega is equal to 0. So in our numerator, when omega is equal to 0, we're going to have 1 minus J0. So that's 1 over something. And then in our denominator, we're going to have 1 minus 0 plus 0. So that's 1 over 1 is 1. At infinity, infinity squared over infinity squared is equal to 1. So what kind of filter is this?
Band stop.
Yeah, band stop. And before we move on to our phase angle here, so I'm going to have you guys verify this in your homework assignment. But when we have this series RLC circuit like this, if we take the output over the inductor by itself, we have a high pass filter. When we take the output voltage to be the voltage drop over the capacitor, you should see that it's a low pass filter. So it makes sense that if you have a high pass filter and a low pass filter, you're going to wind up getting a band stop filter. So you're going to allow some things while the low pass filter is working, and then you're going to stop for a bit, and then you're going to allow high frequencies when the high pass filter starts working. So anywho, and you can get the separation between the stop bands. So like, I'm trying to think of what I mean by this. So the response of a band stop filter, a real band stop filter, practical band stop filter, I guess would be a better way to put it, is going to be something like this, where this guy is omega C1, this middle frequency is omega naught, and then this guy is omega C2. So you can adjust how tightly, like how broad the spectral response is here, or how narrow it is by playing with the values of the parameters. So anyway, you can make it a very, very steep valley or a very, very broad valley by playing around with things. All right, the last thing then would be our phase angle. Erase. And our phase angle theta, come on pen, of omega is, as always, the arctangent of the imaginary bit, which in this case would be 1 minus omega squared LC times omega RC divided by the real, which is 1 minus omega squared LC. And I should probably make mention of something that I'm doing here. I'm only looking at the numerator because the denominator is shared, so those guys are going to cancel each other out. But technically, I should have 1 minus omega squared LC times omega RC divided by that whole numerator divided by 1 minus omega squared LC quantity squared divided by that whole numerator. So I just want to be clear that I'm inherently skipping a step here. So this is going to cancel one of those guys. Did I make a mistake up here? I did. I can't cancel out those C's because there is not a factor of C in the 1. Sorry about that. So this is going to be the inverse tangent of omega RC divided by 1 minus omega squared LC. So we can see that looking at the band stop filter and the band pass filter, their responses are very, very similar, except they wind up being inverted. They have the exact same resonant frequency, they have the exact same corner frequencies, and the phase angle response is literally the inverse relationship. So for the band pass filter, it was 1 minus omega squared LC over omega RC. And here we have the opposite. So that's band pass and band stop. So those are the two filters that you have to have a second order circuit in order to generate, but you can also just as easily generate high pass filters and low pass filters using second order circuits. Okay, any questions on the crazy amount of complex math I've thrown at you guys in the last 40 minutes? All right, nobody's saying much of anything, so I don't really have anything else prepared for today, so I'll let you guys go. I'm going to post your homework assignment hopefully within the next hour, as soon as I finish it up and make sure that I'm asking questions that aren't wildly difficult to solve. As I said previously, if you can get your exam 2s submitted to me by about 10 o'clock tomorrow, I will grade them as well and give you as much information as possible regarding whether or not you should stay in or drop the class. So if nobody else has anything to say, I will catch you guys on Monday when I believe we're going to start talking about 3-phase circuits. All righty, see you Monday.